the last lecture we derived an optimum hyperplane for linearly separable patterns. So, we considered both the primal problem and the dual problem, and we saw how we can solve for the optimum hyperplane based on dual problem. So, depending upon which is convenient to you, you can adopt through the primal route or the dual route and optimize the problem and then solve for the optimum hyperplane. Okay. Now, let us go forward and discuss the situation towards deriving an optimum hyperplane for the non separable case. Okay. So, consider the following cases. I have a 2-dimensional hyperplane, I have a 2-dimensional plane here, x1 x2 plane, and I can have points that lie in this configuration. So, this is my optimum hyperplane indicated by these red dots, and I have points belonging to class 1 and 2, the stars here or the crosses here and these circles like this. So, this is clearly linearly separable, and the points are on the right side of the decision surface, right. The points are on the correct side of the decision boundary. This may not be the case in a second scenario. So, I will just draw the hyperplane first. I can have points which are these crosses that possibly spill over the other side, and I have these circles that are here. So, I have essentially points that are inside this margin, but on the wrong side of the decision surface. They are inside the region of separation, but on the incorrect side. So, I would probably mark this as some of the points. So, obviously, in case A there are 0 errors, in case B it leads to a misclassification, right. This has misclassified points. So, therefore, the error is not 0. Okay. Now, given this situation, we are interested in a formal treatment for non-separable data points. So, let us introduce a new set of non-negative scalar variables, and I call them zeta I equals 1 to n, into my definition of the hyperplane, right. So, into the definition of the hyperplane, I want to bring in this new set of non-negative scalar variables. So, I have di times w transpose xi plus bias is greater than or equal to 1 minus zeta I for I equals 1 through n, and these variables zeta i's, they are called slack variables. And in some sense, this gives me a measure of deviation of a data point from the ideal conditions of pattern separability. So, this gives us a measure of deviation from ideal conditions of pattern separability. So, there are two cases as what we can imagine. For 0 less than or equal to zeta I less than or equal to 1, this is case A, which is here, that is the points are on the correct side of the decision boundary. When zeta I it is greater than 1, it is on it is case B, because this value can be negative, and therefore, you can have these points flipping across the optimum hyperplane. This is the case, second case. For zeta I greater than 1, it corresponds to case B in the figure. Now, you may also wonder where the support vectors lie. The support vectors are those that satisfy the equality precisely whatever be that zeta I, even if zeta I is greater than 0, then the support vectors are those that satisfy the conditions given in this equation here. I call this equation 1, okay, in equation 1. Now, what is important for us is to be able to formulate a separating hyperplane for which the misclassification can be minimized when you average it over the training set, right. Because we have nonlinear separability here and we have misclassified points, our goal would be to minimize on an average this misclassification error rate. So, goal would be to find a separating hyperplane for which the error is minimized when averaged over the training set. So, this is our goal. So, we formulate this problem as follows. We formulate phi of zeta, which is summation I equals 1 to capital N I of zeta I minus 1. So, this I is basically the indication function. So, I of zeta equals 0 if zeta is less than or equal to 0 and 1 if otherwise, right. So, when zeta is greater than 0, this is 1. So, this is our error, because zeta I is, if it is 0 to 1, this quantity is going to be negative. When it is greater than 1, there is no problem, and between 0 and 1 we have this issue where we have points that are lying on either side of the decision boundary, and that leads to misclassification. Now, to make the problem tractable, because we are now dealing with a summation of indication functions. So, what we do is we approximate phi of zeta to be summation I equals 1 to n zeta I. This is what I have. Therefore, I can formulate my objective, I mean I can formulate my Lagrangian that comprises of my weight vector and these slack variables zeta. I would call this to be a vector of it comprises of zeta 1 so on till zeta n. This is half W transpose W which is my objective function, along with the constraint, and this is an equality constraint. So, it is C times summation I equals 1 to n zeta I and this quantity C provides a trade off in the complexity of the machine. It is in the computing complexity of the machine and the number of non-separable patterns. Because this is our constraint. So, one may wonder how to choose C. C can be experimentally determined via the standard training or test set using some crude form of resampling. It can also be determined analytically by estimating something called the VC dimension, which I will touch upon, and then using these bounds on the generalization performance of a machine based on the VC dimension. So there is a way in which you can choose C. So the goal that we have is we need to optimize phi of w and zeta, this function of w and zeta with respect to w and zeta i's I going from 1 to n. That's the objective. So with this, let us formulate the primal and dual problem. So first would be the primal problem. Given the training set xi and di, I equals 1 to n, we need to find the optimum values of the hyperplane, that is the vector w and the bias b, such that the following holds: d sub I times w transpose xi plus bias is greater than or equal to 1 minus zeta I for every constraint I equals 1 through n, and zeta i's are greater than or equal to 0 for all I. So what this boils down is we need to choose the weight vector w and slack variables zeta I that minimize the cost functional phi of w and zeta given by 1/2 of w transpose w plus c times summation I equals 1 to n zeta I, right, and c can be a user specified parameter. So, going by the same way that we took the derivative with respect to and then solve for these conditions. So, now we have this cost functional and then we take this cost functional, put the constraint conditions, these are inequality conditions, we put these inequality conditions and then form the Lagrangian, and from the Lagrangian we take the partial with respect to W, with respect to the bias, with respect to the zetas, set them equal to 0 and then arrive at the conditions, and from the conditions like what we did for the linearly separable case we formulate the dual problem for the non separable case. So, let me write down the dual problem. The dual problem is stated as follows. Find Lagrange multipliers alpha I equals 1 to n that maximizes this quantity q of alpha, which is given by summation I equals 1 to capital N alpha I minus 1/2 summation I equals 1 to n summation j equals 1 to n alpha I di alpha j dj xi transposed xj subject to the following conditions: summation alpha I di equals 0 over all I equals 1 to n and 0 less than or equal to alpha I less than or equal to this user specified constant c for I equals 1 to n. So, notice this change here. In the case of linear separability, we had alpha i's to be greater than or equal to 0, and in this case we are bringing this constant capital C which depends on the constraint that minimizes the misclassification over the training samples. Now, I have deliberately skipped the derivation of the dual problem because it is straightforward. So, once you set up the primal problem and you know the constraints, you follow the exact same steps as we did for the linearly separable case and we arrive at the dual problem. You may be exercising this problem on the homeworks. Note that the slack variables zeta I or the Lagrange multipliers. So, neither slack variables zeta I nor the Lagrange multipliers appear in the dual problem. And the only minor difference is how you bound alpha I to be between 0 and c as against the separable case where alpha I is greater than or equal to 0. We do the same process of optimization and after proceeding with the optimization steps by taking the partial derivatives with respect to the variables in the Lagrangian formulation and setting them equal to 0 and then trying to solve them, we can solve for the optimum value of the vector w given by the same quantity summation 1 equals summation I equals 1 to n suffix s alpha optimum for each constraint I times di xi, and ns here, this is an important variable, this is the number of support vectors. Because this is where you are satisfying the constraints with conditions with equality, right. We had an inequality constraint in terms of zeta I, we had an equality constraint, and where you are satisfying with the equality constraint even if zeta I is greater than 0, and that is where you have to look at these vectors that satisfy this condition and they form the support vectors, and you can compute the optimum hyperplane over these support vectors. And we have this condition alpha I di w transpose xi plus bias minus of 1 minus zeta I, this quantity is equal to 0 for I equals 1 through n, and mu I zeta I equal to 0 for I equals 1 through n, where these mu i's are the Lagrange multipliers to ensure that the slack variables zeta I are non-negative. So, you need to have constraints over the slack variable zeta I. So, therefore, you bring in Lagrange multipliers mu I to ensure that they are non-negative. So, these are some important considerations. So, therefore, if you look at the primal problem, right, at the saddle point, this condition is true, that is the Lagrangian derivative of the Lagrangian with respect to zeta I is 0. So, this implies, so from this constraint condition that we have here, right, alpha I times this condition from this constraint, we land up with alpha I plus mu I equals C. Therefore, zeta I is equal to 0 if alpha I is less than C. So, you can verify these details as part of the homework exercise. So, I think what is important conceptually in our discussions, of course, I deliberately avoided a lot of derivations in this module because these will be exercised as part of your homework. So, the key idea that you have to realize is we introduce these slack variables zeta, so that we consider the case to accommodate the misclassified points, and then we want to minimize the average cost over these misclassified points, and with respect to that we formulate the appropriate cost to solve this problem. We formulate the cost functional, which is half W transpose W plus the constraint that averages these misclassified points, and we want to solve this cost functional subject to these constraints. Whereas in the case of the linearly separable case, we never had the zeta i's, we just had W half of W transpose W, and that was our objective, and we were supposed to minimize that objective subject to some constraints. Here our objective itself has two components. One is this convex function as a function of W, which is half W transpose W, and another term which depends on the slack variables zeta I, that in some sense minimizes the misclassified number of points averaged over all these data sets. And then we formulate a dual problem from the primal problem, exactly following the same steps that we did for the linearly separable case, and with this knowledge we can compute the optimum hyperplane over the set of support vectors that satisfy this condition here that I wrote with equality. Okay. So this is this completes the details for non-linearly separable patterns. Of course, the missing details in this lecture are the detailed derivations to set up the dual problem and looking into the conditions when we formulate the Lagrangian of the primal problem and setting the partial derivatives equal to 0 and then arriving at the appropriate conditions. These will be exercised during the homework, or the interested reader can work these details out, otherwise we will try this on the homework. Yeah, before we end this slide, you know, this is a deba here before zeta I, right. Deba j upon deba zeta I has to be 0, not the d variable here. So we stop this lecture here.